my final year project titled Smart Sense Navigation, a real-time obstacle detection and distance estimation system for the visually impaired. The team members are Abhinayashri, Anirita and Divyadarshini under the guidance of Ms. Rupa Kesavan, Assistant Professor of Sri Venkateswara College of Engineering. The domain of our project is deep learning. Our project addresses the following problem statements. Visually impaired individuals face day-to-day difficulty in navigation in unfamiliar indoor and outdoor environment due to the lack of visual perception. Traditional aids such as white canes and guide dogs does not provide or cannot detect dynamic obstacles in real time. Existing GPS navigation application do not provide obstacle detection, and also it is ineffective to detect the obstacle in indoor or crowded areas. And existing hardware based assistive system uses lidar or ultrasonic sensor, which are very expensive and bulky and cannot be affordable by the visually impaired people. And many vision based solutions depend on cloud processing, which will lead to privacy concerns. So the major motto of our project is that to develop a smartphone-based mobile application which uses AI to detect the obstacle and estimate the distance without requiring any kind of additional hardware. And the output of this project will be a real-time audio guidance which provides direction for the user to navigate in their real life. So the impact of this project will be the improved safety, independence, and confidence for the visually impaired users. So our project was based on this base paper. Here in this base paper, AM Alaste have used YOLO V10 version of machine learning model for object detection and by LSTM multi-head for object classification. So here in this system, they have achieved a high accuracy in indoor object detection and also have employed YOLO based models in CNNs and also in additional hardwares. So the research gap what we have identified here was a need for lightweight and a privacy preserving and a mobile friendly system, and also the integration of both object detection and depth estimation for better navigation. So our proposed solution was a smart sense navigation mobile application, which is a smartphone based real time system which uses YOLO V8 nano version for object detection and MIDAS for depth estimation, since it's a monocular depth estimation, and it uses on-device processing only in order to ensure the privacy and also the audio guidance based on the obstacle distance and risk level. So the issues and challenges we faced in this project was maintaining the smooth real-time performance while processing the camera frames and approximate distance estimation using a single camera and efficient resource management on smartphones, synchronization of AI modules to ensure the proper coordination between the all the modules uh, present in the project, and delivering a clear audio guidance and user friendly interaction. So this is the architecture of a project. The first module will be the smartphone camera, from where the input will be received from the user. The input will be received in the format of a video, and the video will be sent into the pre-processing module where the video will be divided into different frames. So here in this module, the video will undergo pre-processing using the modules present in Python, OpenCV for enhancing the pixels in each and every frames, and NumPy for normalizing the pixels all over the frames. So the pre-processed frames will be sent into the object detection module where we have used YOLO V8 version. Since we are going to deploy the mobile application in a smartphone, we use the nano version of YOLO to have like in order to have less latency. So here in the object detection part, the objects will be detected and the output of this module will be an image with bounding boxes and a class label over the boxes. So the output of the object detection will be sent into the MIDAS module, where MIDAS identifies the distance between the camera lens and the obstacle with the help of the concentration of the pixel in a logic of nearer the obstacle, brighter the image will be. So after detecting the distance, the output will be in the format of an image, class label, and a distance adjacent to the class label. So by estimating the distance like by finding the distance between the obstacles, the risk will be classified based on the threshold logic. The threshold values will be 0 to 0.3 will be the safe zone, 0.3 to 0.6 will be the warning zone, and greater than 0.6 will be the risk zone. So the output will be in the format of an audio such that stating a person is in so and so distance. So these are all the system tools and requirements for software. Uh, for the operating system, we need Android 10 or above, and the programming language we used here was Python, and the mobile IDE is Android Studio. AI framework we used was TensorFlow Lite. For computer vision, OpenCV. For object detection model, YOLO V8 Nano. For depth estimation model, Midas. For audio output, we used text to speech API. And the hardware specification was an Android smartphone with a rear camera greater than 8 megapixels and minimum of 4 GB RAM and a speaker or earphones. So the system is divided into 6 functional modules. Module 1 is a camera input and frame acquisition. Module 2 is frame pre-processing. Module 3 is object detection and classification. Module 4 is monocular depth estimation. Module 5 is obstacle risk and navigation logic. Module 6 is audio feedback system. So here in the module 1 and 2, the input will be received in the format of a video through a camera input. So it captures the real-time frames from the smartphone camera to the monitor from the user's mobile phone. And the video will be divided into different frames, and the frames are sent into the pre-processing module where the frames will be resized and normalized, and the pixels will be enhanced. Module 3 and 4, obstacle detection, classification and depth estimation. So here in the obstacle detection, it detects the obstacles in the captured frame using the YOLO V8 model, and also classifies the objects into different categories like vehicles, bicycles, cars, etc. using the bounding boxes, and the output of this be sent into the depth estimation model where it estimates the detected obstacles and the distance between the obstacles and the user's camera lens to determine the obstacles proximity and the risk levels such as safe, warning and risk zones. So the module 5 and 6 are navigation and audio, and at the end of the entire process, the output will be provided in the format of an audio where the like the navigation decisions will be converted into a real-time voice alerts using text-to-speech technology. So this is the output of our entire project where it displays the SmartSense navigation application applications icon, and here after opening the application it starts to detecting the obstacles present in the frame like a person in 0.77 distance, a bottle in 0.53 distance. So the future improvements we have planned for this project was implementing a real-time visual feedback and debugging, and integration of multi-language audio support to improve the accessibility for diverse users, and also to improve the system performance even under low light condition using the image enhancement pre-processing techniques. So these are all the reference paper we have referred for our project. Thank you.